Something is going to hit the Earth again. There was an impact in Siberia within the last decade that was caused by an object about 20 meters across.
It broke up in the atmosphere and created a big shock wave. It was 10 times the size of the Hiroshima nuclear explosion.
It injured about 1,000 people in the town of Chelyabinsk.
Of course, if you imagine this happening with a greater population density.
The purpose of the DART mission is to take your spacecraft and you ram it into an asteroid to change the orbit so it won't hit the Earth.
We're not just trying to figure out how to deal with what's coming. No, we're actually going to go out there and we're going to try to stop it. Defense is all great, but you do need to score points. Earth gets hit by asteroids and small debris all the time, but most of the asteroids break up in the atmosphere. All of the bigger asteroids have been cataloged, like the dinosaur killers that are 10 kilometers or 1 kilometer plus. At this point, what we're looking for are things that are smaller, that if they were to hit the Earth, they would create a regional impact.
Asteroid impacts that are big enough to cause damage and cause real problems are rare, but the stakes are really high. So the problem in an asteroid impact is that the Earth is going around the sun, an asteroid is going around the sun, and they both want to be in the same place at the same time. It's been over the past 20 years that planetary defense has started to be taken seriously after an impact into Jupiter by a comet in the mid-90s, and this impact into Siberia, I think, also opened a few more eyes. In 2016, the Planetary Defense Coordination Office was set up in NASA to demonstrate that we can do something about an asteroid impact if something is coming in. A nuclear device, for a long time, it has been the only tool that people have considered. But the concern with dispersing an asteroid is that now you have 2 or 5 or 15 things, and the pieces aren't that much smaller. What we want to do is understand those orbits for all the asteroids that might come close to the Earth. Then it becomes a matter of picking the new orbit you want for the asteroid and then changing its speed. If you have 20 or 30 years to do that, then you only need to change the speed by a millimeter a second or less, and then it'll miss the Earth entirely. The purpose of the DART mission as a whole is to test how this technique of a kinetic impactor would work if we ever needed to use it to deflect an asteroid. Didymos is a binary asteroid system, so there's a main body and it has a satellite. And we call those Didymos A and Didymos B. By going to a binary asteroid system for the DART mission, the scale is much smaller. Didymos B is moving around only at maybe 50 centimeters a second. So if you change the speed by a millimeter a second, that is pretty easy to measure, given our capabilities.
The awesome thing is our dartboard, because one should have one, with Didymos B on it. Over here, which is this is the main asteroid, and then Didymos B is clearly where everybody hits. It says the counting down to the time we start the spacecraft INT, where the whole spacecraft comes together. So we're very excited. 163 days is a very short amount of time. It's insane. So DART is launching on a SpaceX Falcon 9 rocket in July of 2021. Each one of the NASA missions has, the main objectives. So our most important one is redirect a moon of an asteroid. Our second most important one, change its rotation period by about 73 seconds. Our third objective is on the ground, they're going to spend some time looking at the rotational period and are able to figure out how much we changed the period. And then our last objective is when we're going to hit it, we're going to create a plume. It's called an ejecta, and people want to be able to measure how much that plume helps push the moon along the way. The DART mission is a technology demonstrator for NASA. We're demonstrating not only our first planetary defense technique, we are demonstrating the next C ion engine, we're demonstrating the rollout solar arrays, which is basically solar cells on big blankets, and they provide a lot of power to the spacecraft, and they're super lightweight. But the most important one, of course, is SmartNav, and that's what allows us to hit the asteroid. Didymos B is about 160 meters, so about the size of the Washington Monument. It takes us about 12 months to get to the asteroid. We're going at about 15,000 miles an hour, which means that we're going to be going from New York to DC in 1 minute. As we get closer in, About 8 hours out, we turn on all our systems. We're starting to stream pictures back to Earth. The spacecraft is still under ground control, though. And at 4 hours out, we turn it over to the smart navigation system.
All we see is essentially one bright dot that might be about 2 to 3 pixels large, and that's the Dynamo system.
All the folks that are going to be in the mock behind me here, they're just going to be listening. They're not doing anything else. And the spacecraft itself is going to control what it's doing, and it's going to target the asteroid.
At 80 minutes out is when Dynamos B starts hopping out from behind Dynamos A, starting out at 1, 2 pixels.
We're trying to aim for the center, but imagine a center of a dog bone. Where exactly are you trying to get to? So what you're trying to do by SmartNav is trying to create an envelope of what do you think this moon might be like. Even though you don't know the shape, parts of it could be completely dark and you don't actually see them, and yet you're still trying to go for the center.